Okay, welcome back everyone in the room and online. So welcome to this contributed session on spatial temporal modelling. We've got 4 presentations in the session, so again we'll be quite tight for time. Okay. So we'll do the same as this morning. We'll just take all the presentations first of all, and then if there's time afterwards we can take a few questions. If not, I'm sure the speakers will be happy to get questions over email or through the networking platform. So first speaker, delighted to introduce Meredith. And Meredith, over to you.
Thank you. Hi, I'm Meredith Franklin. I'm associate professor in the school, the Department of Statistical Sciences and the School of the Environment at University of Toronto. I recently moved from University of Southern California in Los Angeles. So a lot of my examples today are California based. Anyway, I'm going to talk about enhancing machine learning models for spatiotemporal predictions for environmental factors. This work I'm actually showing is going to be focusing primarily on air quality. And one of the driving factors is some issues that we had with the data, and we tried to attempt at a solution for that. So first, a little bit of background. So air quality and health, well, many of you know that airborne particulate matter, which is one of primary air pollutants that of concern, is a well-known cause of morbidity and mortality. Many causal studies have been done of that. The global burden of disease has estimated about 4.1 premature deaths associated with PM. And PM is the top worldwide risk factor, environmental risk factor worldwide. So when we talk about air quality exposure, what we actually want to do is we want to use data that might be measured somehow, and then do some spatial temporal interpolation in order to generate what's so-called exposure estimates so that we can facilitate health effect studies. So, but modeling air pollution is a challenging task. There's complex spatial scales, interactions between components, and dynamical patterns. There's been an explosion of data from a variety of sources, including satellites, which is sort of the main idea of my talk today, monitoring networks and field campaigns. And environmental scientists have been adopting data-driven solutions to modeling these processes rather than really relying solely on traditional deterministic approaches, such as like dispersion models or in the terms of climate type models. And there's a long history of spatial statistical methods that have been used to interpolate data from point locations to generate exposure maps. But really there's an emerging use of, I think we heard a little bit this morning about the use of AI and machine learning from environmental exposure modeling. But a lot of times it operates as a black box. And so some of the other motivation behind this is that, well, air pollution is measured at point locations in developed parts of the world, such as California on the left there. We can see that there's a lot of monitoring stations. It covers fairly well, although there's sort of an imbalance of monitoring within cities. But as you can see from the picture on the right, the networks in a lot of part of the world are very limited. And so relying solely on ground-based measurements is really difficult and challenging, particularly for global related studies. So as a result, a lot of my work has been in integrating remote sensing data into air quality assessment. So really, regardless of the infrastructure, ground-based monitoring doesn't necessarily provide the spatial coverage needed for exposure assessment. But in some parts of the world, of course, we don't have very much at all. And so we would like to be able to rely on something like a satellite. So the satellite that on the left is an instrument that's going to be launching pretty soon called the Maya instrument. And it's basically multispectral. It monitors and looks at the physical characteristics of the atmosphere, but it does so by measuring its reflected and emitted radiation. It has spectral, angular, polarimetric, all sorts of different types of signatures that can be leveraged under complex algorithms that are basically developed by the smart folks at NASA. And what they do is they retrieve quantities that have physical meaning. And so one of the issues is that even though for air quality assessment, the physical quantities that are retrieved are not necessarily exactly what we want to develop our models for on the ground. So one of the problems and challenges in air quality modeling, especially when we start to integrate satellite data, is that we want to relate what's measured optically or spectrally into a meaningful surface level quantity. So not only is it not measuring directly what we want, for many of the satellites for air quality, we look at this measure called aerosol optical depth. And so aerosol optical depth has this property where it's basically detecting the abundance of particles in the total column of the atmosphere related to how the sunlight reflects the particles in that column. And so we want to be able to relate something that's measured from the surface all the way to the top of the atmosphere by that satellite to something that's on the ground, in addition to saying, okay, we have this measure of aerosol optical depth, but we actually want particulate matter. And so we have to deal with that problem. Satellites are not perfect. Yes, they provide spatial coverage over areas where we might not have monitoring, but there's a lot of problem with missing data. Clouds retrieval issues are a couple of the problems. And then, of course, in terms of relating what's measured by the satellite to a meaningful surface level quantity, we're starting to involve a bunch of different sources of data, and all of these sources of data are observed and measured on different spatial, sometimes different temporal scales. And so features that go into the model in order to make these relationships are often spatially misaligned. So we have the data issue of a misalignment, missing data. And then, of course, we also, since we have some holes in the data, we want to be able to spatially and temporally interpolate observed or measured quantities over space and time, which is, our primary problem in spatial and spatiotemporal statistics. So the first problem is the calibration issue. So the satellite has these observations, but then we need to combine it with a whole bunch of other information. We need to kind of cut out the top of the atmosphere. We want just the surface. So we might use some land use information. We might have some emissions indicators to relate to specific locations. We often need to deal with meteorology, which can affect the satellite measure. And then, of course, we want to link it to the ground monitors in order to really understand the relationship between what's being measured on the satellite. And then we might calibrate what's this aerosol optical depth to particulate matter with all of these things in between in order to then sort of have this relationship and then use the satellite information to generate PM estimates. The second issue I mentioned was the missing data issue. This is Los Angeles County in the outline. But as you can see, on one day in 2018, there was very little measurements. The red dots are some of the monitoring locations in the LA area. And then on the right-hand side, you can see a day where there's quite a bit more measurement, but it's never perfect. There's always, some issues with the retrieval. And then the other issue is the spatial misalignment issue. And so this is the issue that has plagued a lot of my work for years. And so this talk is sort of a pet project of mine, where we really have this issue where we have a point measure on the ground. We have satellite data. We have meteorological data measured somewhere else. The issue is that we have different resolutions of grids. We have different supports. We have point, we have aerial, we have different types of data and different grid resolutions. And so how do we actually relate that? So what we normally have done, and this is another picture of Los Angeles, what we normally have done, so all these dots here are places where things have been measured, and then that gray is the grid from one of the satellites, the Miser satellite. What we end up doing is what we have here on the right is we spatially align everything. So we'll say, okay, whatever overlaps our PM monitor, we're interested in aligning all that data with that. And then we're going to build the model on those matched data. But because of a lot of missing data and because of the spatial misalignment data issue, this is not a perfect answer. So we always do this. Everybody is doing this, and we're building different models with this. For example, there's spatio-temporal regression models. We align all the data together, and then we fit this model with spatial-temporal terms, interactions. This is I'm showing this type of model because I've done a comparison from our new method with this. This is it's sort of a generalized additive type model with tensor products for space and time. We use three-dimensional tensor product smoothers, various types of things like that. Or machine learning. A popular alternative right now is to use machine learning, where you have aligned all the data, and we can also, that other model does capture spatiotemporal nonlinearities. Machine learning, as we know, does that too. It can incorporate spatial and temporal predictors to do, and it does a pretty good job, but it doesn't do so in a statistically informed manner. And we're trying to generate physically plausible spatial and temporal predictions, but it doesn't deal at all with this misalignment issue or missing data at all. This is just a picture to show some of the observed data over the region. The aerosol optical depth is sort of in the background, and then the predictions are in the front. We can see that we still have a deal with missing data issues and holes in the prediction surfaces because of these various things. And these are averages, so this isn't even a daily picture. Okay, so the solution that we were thinking of, that we have been working on, is that we have to deal with the spatial misalignment situation and missing data situation. So this is a very simplistic model. The simplistic model is taking our observation Y, which would be, in this case, particulate matter. That's our target, what we want to predict. And then we have all of these predictors. Aerosol optical depth in this case would be our primary one. And then it's going to be, we want to form this weighted distance function in order to be able to say, okay, we may not have a direct alignment with our PM monitor, but we have observed some aerosol optical depth around the area, and we might have measured meteorology at a different location from our PM monitor. So this is basically an idea that we have this covariance-based distance-weighted regression model that basically will take the target and then do a search in an informed manner around to then weight our predictors by a certain distance in order to help inform the prediction. And so we can pick any kind of valid covariance function. We focus on the Maturin covariance function. We did some testing with the exponential covariance function, but we basically have a weight that can be formulated by some valid covariance function. In order, this is a busy slide, in order to test this, what we did was we generated, or in order to develop this model, we basically wanted to relate our outcome with our predictor S. We did this just sort of on a univariate fashion first, with our target in mind of predicting PM from aerosol optical depth. They're going to be weighted by their separation distance. And so we're going to, instead of just employing a covariance function, we're going to employ cross covariance functions. So we are considering a bivariate Gaussian random field where each component is a univariate Gaussian random field evaluable at every location within our finite sample space. We assume non-zero mean, stationary, and isotropy. In this case, these are all things that we're thinking of expanding. And we propose our cross-covariance model based on the Maturin covariance function. And these are just the details of the cross-covariance function that with a positive semi-definite covariance matrix of that form that Knighting published about several years ago. And those are just the model components. So we have the covariance functions, we have the smoothness parameters for both X and Y, and for the co-located correlation coefficient. We have the variances of each univariate random field as well. And we put all of that together. So this is just the sort of the idea of the simulation behind what we will eventually apply in the real data. So we basically simulated several sets of these bivariate Gaussian random fields in order to sort of understand how we might relate PM and AOD and smartly weight them in terms of spatial misalignment. So we set up these observations that are misaligned. You can see on the right here, we have the dots. So that would be our PM field. Basically, that's obviously this is still a simulation, but we selected our PM locations. And then the X's, we say, okay, those are the areas around our point locations. But then we're going to think about weighting our observations within that buffer in order to relate to our target. And so we've chosen various different distances in which we can, maximum distances basically in terms of these sort of buffers that restrict the distance between Y and X to be sort of a physically plausible maximum distance where we could actually see a correlation between PM and AOD. And then additional considerations have been, we've introduced those, and that is both the smoothness and the missingness. So the smoothness of the process and then the missingness issue that we have with the satellite data. So we replicated the intended use case where we had the coincident input data were missing, but neighboring input data were available. We tested this with different rates of missingness. In this case, what I'm showing here is a rate of 35% missing. And then we also tested whether the difference in the smoothness played a role, and we examined different levels of smoothness in nu1 and nu2, as well as the correlated coefficient, co-located correlation between X and Y, or AOD and PM. So what we see is that, so this is just a box plot of a whole bunch of different model results based on the different smoothnesses and the different correlation coefficients. So if what we CDR is our proposed model, and then we compared it to a GAM model, the one that I showed initially, and on coincident aligned data, and a linear model also just on coincident aligned data. And what we see is that the CDR model, this distance-based regression, performs equally, if not better, depending on how smooth the processes are in order to, in terms of relating X and Y and creating this model. So we do see, for example, here when nu2 would be our covariate, our X smoothness when it was a little bit smoother. And this would be our, when our AOD is a little bit rougher in terms of smoothness parameter, and then PM is a little bit smoother. We actually see that we have a very increased performance for this distance weighted type of approach compared to a GAM model or a linear model. And then this is just to show, so we did this application, and this is just to show the distance sort of weightings that come out. So in this case, we're just showing a sort of a distance exponential decay curve in terms of the weighting on how far we go out. So I have to wrap up quickly. This is just some, including some meteorology also improved our models. But in terms of machine learning, so this is all a very, very good idea, but then we actually still see higher R squareds and better performance in machine learning. So what we've actually done is we've incorporated this distance-based weighted function into a random forest model. And we see modest improvement when we actually have AOD available at coincident. But then when we have to go out to a further search area, we do see when we incorporate this that we have a much, not a huge improvement, but we do get an improvement in our R square. And then we can see from our variable importance of this sort of example with a random forest that our distance-based calibration of the AOD, putting that in a random forest actually was the most important variable, and it did provide some improvements. So in summary, remote sensing observations provide data on environmental phenomena that we wouldn't be able to measure in places that we can't measure them. However, we need to do a lot of statistical magicry in order to use these aerosol observations from satellites. We have spatial misalignment, missing data issues, but adapt this distance-based cross-covariance into a regression framework. We basically can increase the amount of data that we use for modeling, deal with the fact that we don't have coincident data on these different levels of data. And then integrating that function into the machine learning shows a lot of promise. It did, and then it also allows us to use a lot more data in terms of building our models. And then the predictions are a lot easier as well, because we can have predictions where we may not have observations of the aerosol optical depth. So we want to do a little bit more work on examining additional distance weights in higher dimensions, plus incorporating time into that cross-covariance function in order to say, because sometimes we don't have daily data, we might want to have some interpolation in time as well. All right, thank you to my students and to all my collaborators.
So much, Ed. It's really interesting. Yeah.
Thank you.
So our next presentation is by Ala online. Ala, do you want to try and share your screen?
Yes. Okay. Is this clear?
It's just coming through. Yep. Do you want to make it full screen for us?
Okay.
That's perfect. So we can see your slides and we can hear you. So next we have Ala El-Kadi, and we'll pass over to you, Ala, when you're ready. Thank you.
Thank you so much. I'm really glad to be here today. Thank you for having me today. We're going to talk about multi-scale geographically weighted quantile regression model developed by myself, Abdel Nasser Saad and Amira Al-Ayouti. It's a spatial model, so we are more interested in spatial data, which are observations, one or more variables taken at different geographical points or areas, where it is more, where it properties of being spatially autocorrelated and non-stationary, for which traditional regression models cannot be used because it breaks assumptions of traditional homoscedastic and independent errors. That a class of geographically weighted regression models was developed. Geographically weighted regression model is a local spatial model that explore and examine the relationship between the response variable and a set of independent and describe the relationship and how it might vary graphically. Can be expressed by the following formula. Estimated geographical location in the study region, where U and V are the geographical coordinate for that specific location I. Data are local regression coefficients for variable for the location I. It is estimated using geographic weighted least square method, where the weights represent the proximity of the observation to the regression point we are interested in. in the logic that mere observations are assumed to have more influence than further observations, and that decrease in the weights assigned to each observation regarding to its distance to the regression point is determined according to a weighting function or a kernel function. The kernel function, in turn, is determined using a bandwidth, which determines the number of neighbors to be included in the model. So determining the bandwidth value is very crucial in graphic weighted regression model in general. The model was very beneficial in a range of areas. It only quantifies the average behavior of the response distribution, while in many applications, interest actually lie in estimating and studying different percentiles of the entire distribution of the response variable. Therefore, geographically weighted quantile regression as an extension to the geographic weighted regression model, where it explores simultaneously the unity and spatial non-stationarity, but for the entire distribution rather than just the mean for the response distribution. It operates two important statistical approaches, which are geographic regression, of course, and quantile regression. So by extending the geographic weighted regression model to a regression framework, the resulting model is formulated, where the model is estimated for regression location, but for any specific percentile of the response variable. And in this case, the betas reflect the local regression quantile coefficient for that specific quantile. It measures the change in the specified quantile of response variable as the independent variable changed by 1 unit. Another drawback in the geographic weighted regression model is that the covariates are assumed to have a constant bandwidth, or they are assumed to behave on the same spatial scale, which is not really realistic in spatial analysis. Ham et al. 2017 developed multi-scale geographic weighted regression, which drops single bandwidth assumption and allow different covariates to have different bandwidths and to vary different spatial scales. The model takes the following form, where the subscript BW indicates the bandwidth specific for that specific covariate, including the intercept. Geographic weighted regression was a huge advancement in the geographic weighted regression based models, but yet similar to the geographic weighted regression, it quantifies the average behavior of the response distribution, which, as said, may not be applicable. Interest lies in describing the spatial pattern of the entire distribution of the response variable. So to wrap this up, we have two important extensions for the base geographic weighted regression model, one of which is the geographic weighted quantile regression, study the entire distribution of the response variable, but yet assume just a constant bandwidth or spatial scale for all the covariates. And on the other hand, we have multi-scale geographic weighted regression, which assumes varying scales for covariates, which is logical and more applicable for spatial data, but still it study the mean distribution of the response variable. So our modification is to these 2 points together and make a model that studies the entire distribution of the response variable. In the same time, it assumes different bandwidths and varying relationship for different covariates, for which we call the multi-scale geographically weighted quantile regression. So we extend the multi-scale framework to the geographic weighted quantile regression model. The model will be formulated as shown. In this case, we used the backfitting algorithm technique to estimate the coefficient. Backfitting usually is used in generalized additive models, with models where the response variables depend linearly on some unknown smooth function of the predictors. And following the logic of GAMP, we will define the model in this form. It's just summation of some additive term, where each additive term is the coefficient multiplied by its corresponding variable. And so the proposed algorithm will move as shown. For each specified quantile, we will initialize all the additive terms by estimating or fitting a standard weighted quantile regression. Calculate its residuals, which is y minus summation of the fitted terms, and then we're going to regress the residuals plus the additive term for that specific variable against the variable. Using, of course, the standard geographic weighted quantile regression, the estimates for this specific variable will be updated, and then we will have an output of the bandwidths of the specific relationship between the case covariate and the response variable at the Taos quantile, and an estimate for a new estimate for the coefficient. specific covariate, and then we're going to move to the next variable and so on until we reach the last variable in the model. Then it's considered one iteration. The iterations will continue to work until it reaches convergence according to a certain convergence criteria. This is the algorithm we developed, and to test such algorithm, we conducted a simulation study where the data generating process is a standard geographic weighted quantile regression where we have 3 independent variables, the intercept, and 2 independent variables. The region we used is 25 by 25 lattice grid, which constitutes 625 or observations. The parameters, of course, we have 3 parameters reflecting different level of heterogeneity: 0 for the intercept, low for the first variable, and high heterogeneity for the third variable. The initial terms, as said, are initiated from a geographic weighted quantile regression estimates. We did the simulation study at 3 different levels of quantiles: 0.1 or the 10s, 50s, and 90s percentiles. The bandwidth is automatically selected inside the algorithm using the consolidation criteria of the leave one out, and that weighting function or the kernel function used is a bi-square kernel function where dij is the distance between each 2 observations I and j, and is the bandwidth. The results are as follows for the bandwidth selection and comparison between the geographic weighted and the multi-scale. The geographic weighted quantile regression did not accurately identify the 3 levels of different scales of the 3 covariates, as it only gives single bandwidths for the 3 variables, either more close to the one of the variables or just a range between the 3 bandwidths of the 3 covariates. While in turn, on the other hand, the proposed model or the multi-scale geographic weighted quantile model correctly identified the 3 spatial scales represented by B node for the intercept, B1 for the first variable, and B2 for the third variable. Regarding the intercept across the 3 quantiles, it's very evident that it identified the fact that it has 0 heterogeneity, which the bandwidth was almost 624 observations out of the 605, which indicates a good process. And if we have a closer look for the second and the third bandwidths of the second and the third covariates, you can also see that these 2 covariates exhibit more local spatial scale, yet the third variable is more locally, or it has a higher heterogeneity relative to the first bandwidth, and the model was able to differentiate between these 2 across the 3 different quantile levels. Another way to compare between the 2 models is to study its ability to replicate the 3-parameter surface or the 3 coefficients using the root mean square error. From this graph, we can see that across the 3 different quantiles for the 3 coefficient parameters, our model performed much better than the standard geographic weighted quantile regression, especially at higher quantiles, and that may be due to the fact that actually bandwidth and geographic weighted quantile for higher regression is very large, does not really reflect any of the lower or more local scales of the other variables. That can also be visualized using the parameter surface. We have the first row is the true coefficient heterogeneity, 0. The second is for geographic weighted quantile, and the last for the multi-scale geographic weighted quantile using one dataset. It's obvious that at the 10th percentile, that both models can replicate the parameter surface with the superior ability for the proposed model, and for the geographic weighted quantile regression for the intercept is not very good. That is due to that the bandwidth is actually closer to the local spatial rather than the intercept. For the 0.5 or the 50th percentile, we can see that both actually accurately, to some extent, replicate the 2-parameter surface, with our proposed model even better. And the 90th percentile, it's evident that geographic weighted quantile regression was very poor at replicating the surfaces, very large events, while our model still replicates the parameter well. The last criteria of comparison between the models, along with quantile regression, is the goodness of fit. We used here the Bilnoff function, which is defined as follows, which is the weighted absolute residuals, is the mean summation of this function. we could not use the residual sum of squares due to the fact that we use quantile regression. And after calculating this method through the simulated data sets for the three quantile levels, it's obvious that generally the quantile regression is for the models in general, while our model is better in the three cases. It was better fit in the cases. After finishing the simulation study, we applied the model on an application on children malnutrition in Uganda. So the response variable we used is measured as the percentage of kids under 5 who experience stunting across the 112 districts, but actually our sample data only consisted of 94 districts. We conducted this analysis for 8 explanatory variables, but I'm just, due to time constraint, I'm gonna show you the result for one of the variables, which is the mean annual journal temperature across districts. Here we can see that across the 3 quantile levels for geographically weighted quantile regression, which is only have constant bandwidths for different for all the different covariates in the model. In the first in the 10th percentile, the bandwidth was 93, which is more global, which behaves more globally. While in the multi-scale geographic weighted quantile regression, the bandwidth was 23, indicating more localized relationship, which is actually evident from the map where adjacent locations behaved similarly. In the 5th percentile, on the other hand, actually the geographic weighted quantile regression constant bandwidth was 53, indicating a medium local relationship between the variable and stunting percentage. While in case of the multi-scale geographic weighted quantile regression, it was quite close to that number, which is 37 neighbors to be used. While for the 90s quantile, the geographic weighted quantile regression still had a constant bandwidth of 93 neighbors, while for the multi-scale geographic weighted quantile regression, it became more global, or it had more global effect of 72 neighbors to be used, while also obvious that mean annual diurnal temperature had an effect at lower percentile of the stunting percent rather than higher percentiles. So just to conclude, the model, proposed model, to provide a better fit in describing the relationship between different covariants using different spatial scales at different quantiles, which was meant to do. But on the other hand, we found some limitations in the fact that it's extremely computationally intensive, and we need more model diagnostic significant testing techniques to more validate the ability and the usefulness of this proposed model. And thank you so much.
Thank you so much, Ella, for a really interesting presentation. Thank you.
Thank you so much. Thank you.
So our next presentation, we're moving back into the room, and we have Pratik Nag. Yeah, great. So next, Pratik Nag, take it away.
Yeah. Hello everyone, I'm Pratik. So I'll be presenting one of my PhD projects here. So it's called Efficient Large-Scale Non-Stationary Spatial Covariance Function Estimation using Convolutional Neural Networks. So general additive model for the spatial scenario can be seen in this way, where ZS is the spatial process which is observed over locations S1 to Sn, and we can write it is in this like additive format, where the mu is the mean function, and then there is this ys underlying process and nugget effect epsilon s. So this ys can be like a Gaussian marker or any other random field with a covariance function c. However, in environmental and ecological applications, non-stationarity is like a very generic assumption, and which can be incorporated in the models through covariance non-stationarity. So one class of such non-stationary covariance model is this non-stationary matter and covariance function. So as you can see, it's a pretty big equation. So here are several parameters which are spatially varying. So here I have written these parameters in this format. So in total, they are in this capital sigma, which is basically the I haven't yet written the explanation of the capital sigma. So this is basically like a 2x2 matrix of the so it takes into consideration the spatial anisotropy as well as like the spatial range parameters. So you can put two spatial range parameters like sigma lambda 1 and lambda 2, whereas the spatial anisotropy can be considered in like angle phi. So like these are more generally explained in the in my the paper which is there in arXiv. So all these spatially varying parameters can vary, and it can make a more generic non-stationarity in the dataset. So now for the estimation of this like non-stationary kernels, so there are previous methods which are like local stationary and weighted local stationary methods. The like main assumption of all these methods were basically like the whole region, the whole non-stationary region, they are choosing some sub-regions which they are thinking as stationary regions, or like which behaves like a stationary region, and they independently model those regions at once. They don't generally like model the whole region as a exact Gaussian likelihood. So it's kind of an approximation from the exact computation. And also another thing is like for large scale data sets, which is the case for non-stationary matter and field. So if you're looking for like the whole of US, the data set might be a very large data. And then in those cases, like the Cholesky factorization for this computation of this covariance function in the matrix. So the Cholesky factorization will cost like an O(n) cube of performance complexity and O(n) square of memory space complexity. So the spatially varying parameters is another thing which are so they generally in all these local stationary or weighted local stationary methods, they generally model these spatially varying parameters by estimating those parameters in those subregions. However, they are not choosing the subregions in a data driven format. They just choose the subregions in a very subjective way, just by looking at the data sets in most of the like previous work scenarios. Now so this is like whatever has been done till now. So we implement the non-stationary kernel in the exageostat. So what is exageostat? Exageostat is a high performance software which is which has been developed in 2018 by Abdullah and al. So they have created this software which can do parallel computations, as well as like with the help of GPUs we can do exact Gaussian likelihood computations for very large scale. Like even in so in this paper and in some other papers, like last year there was one paper which has been published in a conference in SC. So there we have computed till 18 million locations for like the Gaussian likelihood computation, and that computation is like an exact computation. It's not any kind of approximation. So we use the supercomputer in KAUST to do that calculation. And yeah, so here the exageostat software basically runs on this Spatio runtime system, and also like there is a software called Hodler which has been developed in like the supercomputing facility inside KAUST. So they use this parallel computations. So we are using those softwares in Exagiostat to give us this parallel task-based parallelism. Now for the covariance parameter estimation, so here I explained that these are the spatially varying covariance parameters. So, but like to estimate those spatially varying covariance parameters, they are varying over like the whole space. They are like in each and every location. So we have to find some node points in those in that whole space where we can choose like those spatially varying parameters to be some values, and then those spatially varying parameters based on those node points can vary. So here we are exactly doing that. So we are basically like based on these local likelihood methods and whatever they were doing. So here what we are doing, we are not doing a local likelihood. Instead, we are choosing some subregions and then taking the node points for those subregions and then estimating the parameters in those node points. Now, once the estimates are there, we can do a kernel convolution like this and get a spatially varying space. So the parameters will be continuous in space. It will not be like a step function or any other kind of function. And instead of just estimating this like spatially varying parameters like at the starting or at a separate manner, we can incorporate this whole thing, whole architecture inside the estimation process, so that every time when the parameters get estimated, it will actually create the this like spatially varying space, and then it will do all the calculations. So the log likelihood will be actually calculated on like the spatially varying parameters itself. So now then we are basically using the Gaussian log likelihood here. So there is nothing else that we should explain. Now, using this spatially varying kernel, we did generate a synthetic dataset just to showcase. So here, as you can see, like we splitted like in a 4 subregion based format. We did generate the dataset, and as you can see, like in the bottom left part of the space, it's like here the spatial range was smaller as compared to the top right. In the bottom left, so you can kind of see from the visualization that the data values are changing much faster as compared to the one in the top right. So the model is kind of giving very good synthetic simulated results on the like data set generation. Now here comes the next part. So here I discussed about this one. So the subregions are subjective and they are not data driven. So how should we choose the subregions of this whole data sets? So we are proposing a framework which is based on convolutional neural networks. We call it ConvNet. So this framework can be standalonely used to identify stationary and non-stationary spatial fields. And also this this framework, we have implemented it inside our Exagiostat frameworks to identify those subregions, those stationary subregions from the non-stationary random field. So this convolutional network, how it basically works is that we take photos in our mobiles generally, right? And we also do like different kinds of filterings on those photos. So this convolution is basically that thing. It basically does like a stride-based matrix multiplication. It can be either a 2x2 matrix or a 3x3 matrix, and it multiplies over all the pixels of this image and creates a set of several layers of images. So if you multiply with 32, so here in our case we multiplied with 32 such matrix configurations, and then it created 32 such images. So this is like one stage of construction of the convolutional neural network structure. And then at the final stage, it basically gives the probability of the non-stationarity. So this is just the mathematical explanation of how the convolutional neural works. So now for the training of the CNN model. So we know like in real data, whichever data is coming, whether it's a stationary or non-stationary, we don't know. So we have to train the model on some synthetic data sets. So to get the synthetic data sets, how should we choose the synthetic data set? So we have explained that more in the paper. So what we have done is that for the non-stationary kernel, we chose like this non-stationary Mattern implementation here, through which we were generating these synthetic data sets, as well as we actually chose several other kinds of non-stationarity, which can be done through like this computer simulated functions. So those gave us a very generic set of non-stationary kernels, and as well as for stationary kernels, we use the stationary like Mattern Gaussian process, and as well as the exponential and other stationary kernels, to give us like two sets of distinct and large data set regimes for training. And then we so in most of these data sets which we generally get, these are like the real data and also the Gaussian process and other processes like the random fields. They are not in a grid format. However, for like running a convolutional neural network, you need a grid. So to get that, we pre-process the data sets into such a way that all of these data sets that we are generating, whether it's real or it's coming from some synthetic field, we can grid it into a 100x100 grid format. This is how, like, one example of like how the pre-processing looks. So if your data set is something like this, and then you can do the pre-processing and get the pre-processed data. So the details of the pre-processing, it's like a mathematical framework that's just like taking a kind of neighborhood approach to do the interpolation. So, and then performance of this convolutional neural network. So we used this convolutional neural network on several like stationary and non-stationary data sets as test data sets. And as you can see, this is like the non-stationarity probability. So the model here was giving like the probability of non-stationarity, like how non-stationary is the field. We just found that probability. So that probability here, as you can see, like this is on the x-axis the probability, and in the y-axis the relative frequency of each of the data sets. And it quite nicely identifies like the stationary data as well as the non-stationary data, like based on the probabilities. So for non-stationary, it gave like very high probabilities, and for stationary, the probabilities were very low. Now, so how are we actually incorporate this convolutional neural network in the exageostat framework? So to do that, we basically propose this algorithm. So as we earlier discussed, that these Z1, Z2 essence, these are basically the like the observations and on locations S, and then we choose some anchor locations S1, S2, Sk. So this subregion is then like chosen in such a way that we first choose like there is within this iteration set of values, we first choose a set of anchor locations, and then we do all the processes like pre-processing, and then use the convolutional neural network to get us the probabilities. And like this we do like say for example here K. So we do this kind of things in K iterations, and then out of those K iterations, like we are getting the probabilities for each of those iterations. Then out of those K iterations, whichever the probability is highest, we are choosing that, whichever the probability is lowest, we are choosing that section as the best possible choice of the non-stationary subregions. So now, like instead of being a subjective subregion, we have like a more data-driven way to obtain the subregions. So here are some simulation studies. So here I just showed the parameter estimates. So these were like the spatially varying parameters. So in our simulation studies, we have used like the spatially varying sigma, the range lambda, and the smoothness nu. So these spatially varying parameters were looking like this, whereas for like a non-data driven way and a subjective manner, if you just split the data set into like either horizontally or vertically in a way, then you will end up with the parameter estimates which will look like this. However, if you choose this convolutional neural network framework on top of your modeling, and then you do the parameter estimates, then you will end up with this kind of parameter space, which is basically following the true parameter configuration. This is for another, like for two subregions. So like this, more other simulation scenarios with more generic frameworks have been given in the paper. You can just look into that. I will share. And also the real data application. So we implemented this.
We need to stop.
Okay. So this is like just one thing here. So as you can see, like from the data set, it is very it is kind of visible that the data set can be split in these three formats, and actually the convolutional neural network model could find these three patterns here pretty well, like the subregions, and then we chose like the results out of it. So these are some of the contributions of this work, and the paper is here in the archive that you can choose. And
Thank you.
yeah.
Thank you so much, Pratik. Sorry, we're just so tight for time. Thank you.
Yeah.
A really interesting presentation. So our final presentation of the session is back online again, and I think we have Jaydev. Jaydev, do you want to try and share your screen for me?
Is it sharing?
It's just coming through. That's us. Do you want to make it full screen?
Okay.
That's great. So we can see your slides and we can hear you. So Jaydev, Gil, over to you for the last presentation of the session. Thank you.
Okay. Thank you for inviting me to this talk. So this work is ongoing work in joint collaboration with Dr. Dorcas from Portland State University, Dr. Ivar Kribben from University of Alberta, and Dr. Yulia Gill from University of Texas at Dallas. I am a PhD student at University of Texas at Dallas, and so I'll be giving you an introduction to how multi-way data how we can estimate how covariance estimation works for multi-way data. So why do any of this at all? Recently there has been just an array of bad news. All the predictions are coming true, and the ocean temperatures are increasing at a great rate, and that is causing even Antarctica to melt. And perhaps our estimates of how much time it will take for the Antarctica ice caps to get affected might be cut short. So it is more and more important to analyze and understand all the tools that use all the tools available at our disposal to do climate science. And some of those tools are difficult to use. And the idea is that when there is complex high dimensional data, you often run into computational and computational issues, and of course whatever you're trying to estimate always doesn't work out well. So the goal is to be able to use to have structures that can help us estimate what we want to estimate. And in our case, we are wanting to estimate covariance metrics. So due to advances in satellite and remote sensing, we have more and more high dimensional data, and it is being generated. And it's no longer just generic vector variate or matrix variate data. There are multiple ways in which the data is dependent. So as you can see, the satellite imagery, high resolution satellite imagery will come in in three color channels, so like RGB data. And if you want to analyze all the details in it properly, you need to have this complex data structure, and you need to keep those structures. You simply vectorizing it won't give you appropriate results. Another example is fMRI data. Recently there has been work done on estimating or finding what is the degree of solar flares that can impact our magnetic uh, basically our magnetic layer. And so a lot, and all of this data comes in the form of tensors. So we need to be able to account for the multi-way dependencies explicitly if you want to understand that. Now, well, so remote sensing produces high dimensional complex data structures. As you can see here, you can have latitude and longitude, but this grid will capture sea surface temperature, and you can stack another grid which captures precipitation, pressure, and things like that. And then you can have each data, like each tensor for every time point. So you can have a multi-way data for every time point. So you get a time series of tensors. So this so in case of covariance estimation, so I mean, usually for SST, there has been a paper in JPL about combining combining different satellite data, capturing the same SST or precipitation data, and how to fuse those together, how to fuse multi-satellite or multi-sensor data together into one data set. And that is a challenge in itself, where covariance estimation is a problem. So it is essential to have good estimates of covariance if we want to be able to fuse different data together. So what exactly are tensors? So they are higher, or you can think of them as higher order abstraction of matrices. Uh, the order of matrix or tensor, sorry, the way, so multi-way basically means the dimensionality. Vectors can be seen as order 1 tensors, matrices can be seen as order 2 tensors, and so on and so forth. I mean, so especially in deep learning, tensors are very important, and to represent that, Google named that deep learning library as TensorFlow. But yeah, this is just some basic facts about tensor. So you can slice and dice tensors in a lot of different ways. If anybody has seen Charlie and the Chocolate Factory, there's a scene where they have the great glass elevator, which moves in many different ways. So you can think of fibers of a tensor as elevator moving across these, that great elevator moving across in different lines and in different columns, rows, or and then you can then you can see slicing of a matrix as sort of moving. If you were in a rectangular building, in a cubical building, then the walls or the floors moving. So you can think of slicing as that. There is a very nice paper if you want to review more high-level stuff on tensors. So I really suggest reading paper by Kolda and Bader. They have a lot of high overview stuff on. So the idea is that, okay, so the next thing is that we have Kronecker sum and Kronecker products. Here, basically, this is a way to decompose matrices or tensors into lower order, lower rank components. So Kronecker sum and Kronecker product. So Kronecker sum utilizes Kronecker product, but yeah, the idea is that they help decompose higher order structure into simpler components. So what are the challenges around covariance estimation of multi-way data? We have high dimensionality, so the sample covariance is very unreliable, which is usually called the curse of dimensionality. We have high computational cost. With the number of modes, the order of the precision matrix increases exponentially, so we will have a very large memory requirement. And then a lot of techniques that deal with a lot of techniques don't deal with the multi-way component of the data. They vectorize the data, which loses its structural properties. So how can we deal with these? Well, as mentioned before, you can assume a Kronecker structure on the precision matrix that you get. So you can, for each mode, you can decompose your precision matrix as a precision matrix of each mode. So if you have a 3-mode tensor, for each mode you will have a precision matrix, and then you take a Kronecker product or a Kronecker sum of these components, and you get a higher order, uh, a complete precision matrix of the entire data that we are trying to estimate for. So Kronecker structure has a very nice property that if with Kronecker structure, basically you increase sparsity. You are able to increase sparsity very naturally. Then under some regularization conditions, we can apply lasso, and we can solve for the pseudo negative log likelihood function, and it provides there's literature on this that there's proof everything that this provides a very good estimate. Previous work that has been done on this Kronecker structure with lasso penalty, L1 penalty. There has been few previous works that have been done. Notable ones are Terra Lasso, where they instead of taking a Kronecker product, they use a Kronecker sum, which gives a greater degree of sparsity and a better structure. The other paper is Siglasso, which assume a Sylvester equation for their data generation process. However, most of the work, while they do have a component of time data, they have n independent and identically distributed over time. So they don't have any concept of correlation or any notion of dependence between their data points or data tensors. So usually spatial temporal data violates the IID assumption. They usually are not independent, and so the work that we are doing now is trying to relax those assumptions. So if you can see, this is how Kronecker product or Kronecker sum structures generally look like. They have this very nice pattern to them. Most of these are sparse, so you only see the highlighted points where there is significant covariance or correlations. So our contribution is that we want to relax the IID assumption, and we do this by taking a data generation process that comes from exponentially decaying row mixing process. The good thing about exponentially decaying mixing process is that you can think of IID cases as a special case of mixing process. So if you have fast enough decay, we can often do a lot of things like strong law of large numbers and CLT are applicable to mixing processes just as well as they are for IID cases. So we assume exponentially decaying mixing process and under some regularity conditions, so that we get positive definite covariance matrix, and invertibility and all those things are taken care of. We assume sub-Gaussianity over tensors, which basically says that it puts a cap on the tail, so you can treat it as Gaussian. Then maximum element of a tensor is bounded above. Eigenvalues are positive and bounded. Sample covariance is positive. So these are all things that we need to use to provide asymptotic convergence. So we have done that in our paper. Other than that, so applications, currently one application that we do have that we have is that we applied it to financial data set where so cryptocurrencies have this, the multi-way structure of cryptocurrencies is that cryptocurrencies have some features which give us volatility, but their volatility also varies over different exchanges. So we wanted to see if we can incorporate that dependence and if we can use it for optimal portfolio, and we got some better results compared to previous work. For so but we want to extend this, extend the applicability of the weakly dependent to spatio-temporal data in climate science. And for that, we have a sea surface temperature data set. So, for sea surface temperature, in sea surface temperature data set, so this is an experiment that I ran, and this is for different levels of lasso. So for two different levels of the lasso variable, the lasso constraint. So right now we have a right now for our testing we have done a for 50-week time series of 10 cross 10 tensors, because the SST data set is very large data. It has over 11, I think 11 billion data points. So I had to scale down, I had to cut down the time period. And so I took 50 current, so 50 latest weeks for the data set. And I also took between a latitude and longitude range of 1 and 10. So this is the...
JDev, I'm really sorry, we're out of time. Could you maybe wrap up for us, please?
Oh, yeah.
Thank
So
you.
this is what we have. So some of the future work is that using estimated precision matrix, we want to do multivariate vector autoregression models, and also leveraging different mixing properties to relax the IID assumption further. An application to spatiotemporal data sets, especially aligning different geophysical signatures such as chlorophyll, precipitation, and other over the same spatial horizon, but varying over time. So thank you, everybody.